So, let's talk about a pretty wild idea that could make AI models run insanely fast. It's a total shift in how we think about them. What if we stopped treating AI models like data that a program has to read, and instead, we turned the model itself into pure, lightning-fast code? Let's get into it.
To really get to the bottom of this, we have to start with something super basic. It's easy to just think of our computers as magic boxes, but really, deep down, they are just ruthlessly efficient machines. And the way they handle simple, everyday math actually holds the secret to speeding up even the most massive AI.
And that brings us right to our first stop, a simple little computer trick. This is something CPUs have been doing for decades, and it's the foundation for, well, everything else we're about to talk about.
Okay, so take a look at the difference here. On the left, you've got your standard math, y equals y plus x. To do that, the computer has to create a temporary little holding spot for the result before putting it back. But look at the right. Y plus equals x. We call that an in-place operation. The CPU just directly updates the value right where it lives. There's no extra step, no wasted motion. This is how processors are built to work at their absolute peak efficiency.
So why do we even care about this? Well, because doing things in place is just fundamentally better. It means the CPU is running way fewer instructions, it doesn't have to waste time juggling temporary storage spots, the program itself ends up being smaller, and the result of all that? Everything just runs faster. It really is the gold standard for performance.
Okay, so we've got this hyper-efficient computer trick. Now for the fun part. What happens if we take that exact same idea and apply it to something as huge and complicated as an AI model? This is where things start to get really, really cool.
So here's the big question, right? What if we took all the weights in a neural network, the billions of numbers that are basically its brain, and we stopped treating them like data that has to be loaded from memory? What if we applied that whole in-place philosophy to the AI itself?
And this slide just lays it out perfectly. The normal way, AI as data, means your program is constantly having to go and read these weights from memory, which is slow. The new way, AI as code, is where you compile the model so the weights themselves become part of the actual instructions. So instead of an instruction saying, hey, go multiply by whatever number you find over in memory, the instruction literally says, multiply by 5.237. The weight is baked right into the code.
And yeah, there's a name for this whole thing. Ahead of time, or AOT, compilation for neural networks. We're not just running a generic program that uses a model anymore. We are running a super specialized program that is the model. There are no memory lookups for weights, which means it can be just blindingly fast.
Okay, I know what you're thinking. This sounds almost a little too good to be true. And, like any big, revolutionary idea, there are some pretty real technical hurdles we have to get over. So let's get into the reality of making this happen.
So here's the catch, the big gotcha. A single line of machine code, an instruction, has a physical size limit. You literally can't just stuff an infinitely huge or super precise number into one command. This is what's called the instruction encoding limit. It's a hard physical boundary on how much info each instruction can hold.
And that's where you get this trade-off, right? The pros are amazing. You're not reading weights from memory, which means you get blazing fast execution. It's perfect for the CPU's super fast local memory, its cache. But the cons? They're serious. The final code size can be absolutely massive. You have to completely recompile the whole thing every time you want to update the model, and you are always fighting against those instruction encoding limits.
But, of course, there's a really clever workaround. It turns out that for AI inference, that is, just using a model, not training it, you often don't need ridiculously precise numbers. 16-bit numbers are more than accurate enough to get great results, and here's the key. They're small enough to actually fit inside those instruction limits. We can bake them right into the code. Okay, so with that in mind, how does this whole idea apply to the biggest, baddest models out there today? Let's talk about transformers, the architecture that powers all the big, large language models.
So deep inside a transformer, at its very heart, is this thing called attention. And what it does in its most basic form is for every single word or token you feed it, it calculates a score for how relevant every other token is to that one. This all-to-all comparison is what makes them so incredibly powerful. But it's also their greatest weakness.
So what does that actually look like at a massive scale? Well, if you have a context window of 1 million tokens, the model has to compute an attention matrix that is 1 million by 1 million. That is a trillion relationships it has to calculate.
And that matrix?
1 trillion numbers? Even if they're just 16-bit numbers, you're looking at 2 terabytes of memory. 2 terabytes, just for one part of one layer in the model. I mean, that's just an astronomical number that doesn't fit in any hardware we have today. This is the bottleneck.
So a bottleneck like that, it forces you to stop and think differently. If we can't just keep throwing brute force at the problem, we have to get smarter. And this leads us to what could be the future of AI, one that builds on this idea of compiling models and making their very structure more efficient. Now you might be wondering, hey, why not just mathematically squish all the layers of a model together into one giant simple one? Well, the reason we can't do that is because in between each layer, there are these things called non-linear functions, and they are absolutely essential. They're what let the model learn really complex patterns. Without them, a 100-layer network would be no more powerful than a single-layer one. They make the model smart, but they also stop us from just simplifying it away.
So if we can't just simplify it, what's the next move? Well, this slide kind of shows the path forward. Today, AI models are uniform. Every single layer does the exact same kind of work. But the future? It could be heterogeneous, where each layer actually learns to use the most efficient set of tools for its specific job inside the network.
I mean, just think about it. You could have a model where every layer is different. One layer might need that expensive, full attention, but the next one could get by with a cheaper, sparse version, or maybe none at all. Another layer might pick a faster activation function. Some layers could even learn that for a certain task, they're not even needed and can just be skipped entirely. And then, a smart compiler could look at this unique, custom structure and generate perfectly optimized code for it.
And that really is the heart of it, isn't it? Scaling isn't dead. The way we've been doing it, just more data, more parameters, more computers, that's not the only path forward. There's this massive untapped frontier of just making the models themselves and the code they become fundamentally smarter and more efficient.
So I'll just leave you with this final thought. What if we're on the edge of a new era for AI? One where the models don't just learn the answers to our questions, but they also learn the fastest, most efficient computational path to find those answers. It's a future where the AI literally helps design the perfect software for itself to run out.